All right, so yesterday we talked about all the different types of energy, and in part of that lesson we were talking about, when you put a hot object in next to a cold object, the energy always flows from hot to cold, okay? And that was the start of what we call thermodynamics, okay? Thermo meaning energy, dynamic meaning change. So today what we're going to do is look at the laws of thermodynamics. Right? There's only two, okay? They're really easy. You already know one of them. Right? The first law of thermodynamics is the law of conservation of energy. Energy can't be created and it can't be destroyed. Okay? So that one everyone's fairly familiar with already. Okay? The second law is the one that's going to kind of pertain most to what we're doing in this unit. Okay? And that one describes the direction in which energy travels, which is what we talked about yesterday. Always from hot to cold. So we're going to kind of look at that as well as some of the applications of that today. And to do that, we have to kind of get some terminology out of the way. All right? So the first thing we have to talk about is the terminology. Okay? And the first term is the definition of a system. Okay? So a system is a set or a series of interconnected parts. Okay, and then underneath that, the thing we need to know about systems is that you define the boundaries of that system. Okay, that's what it means by arbitrary. You can choose whatever you want. Okay, there's no rules to where you define the beginning of a system and the end of a system and the beginning of the surroundings. Okay, which is the next thing we've got to talk about. Right? There's a system, and then there's everything around it that's not part of it. That would be the surroundings. So a simple example of that would be, one person in this classroom would be the system. Everything else in the classroom would be their surroundings. Okay? And energy is going to flow between the system and the surroundings. Okay? Now, if I wanted to redefine that, I could say this room is a system, okay? And the rest of the school would be the surroundings. Right? That's what they mean by arbitrary. I can define the boundaries anywhere I want. Okay? I just then have to go, okay, energy is here, that's the system. Energy is out here, that's the surroundings. Okay? Everybody kind of with me on that? Okay? So the parts have to be connected. That's the thing. There has to be some connection between them. So like a semi-truck, like the tractor part and then the trailer, that would be a system because they're connected, right? Everything outside of them would be their surroundings. That would include, so the system, the truck and the trailer, would include also all of the cargo inside the trailer because that is within the boundary that I defined. I said the truck and the trailer were the system, so that means the driver, the cargo, okay? The wheels, the tires, the engine, okay, all of that stuff.
Please excuse the interruption. Could the golf team come down for your team picture? Thank you.
Okay, but the road would be the surroundings because it's not connected. Okay, it's not part of the system that I define. The air around it would be surroundings because it's not part of the system that I define. Okay? All right. So there's three kinds of systems. I'll give you a minute here to copy down the three kinds of systems and then we'll talk about them. All right, so copy down open system, closed system, and isolated, and then we'll talk about it. All right, so the three types of systems are defined by how they interact with their surroundings. Right? An open system interacts freely with its surroundings and exchanges both matter and energy with its surroundings. So right now, you are an open system. Okay? You're breathing in the air from the surroundings, you're exhaling it back out. Okay? You might drink water from the fountain. Okay? All that, you're exchanging matter and matter with the surroundings. You're also exchanging energy. Okay? The heat's off in this room, I'm using you to heat it. Okay? Because you're 37 degrees Celsius and the room temperature is 20. Okay? I know that energy will flow from you, the hotter object, to the surroundings, the colder area, okay? And that will naturally raise the energy of this room, okay? By period 4, it'll be 25 degrees in here, okay? And that's just from people being in here.
Please excuse interruption. Could the junior boys volleyball please come down for your pictures?
Yeah, I keep getting old. I lost my train of thought. Okay, so you'll exchange energy with your surroundings because you are the hotter object, okay? There's no way to seal you off from the surroundings, okay, in terms of your energy. Now, if you were a closed system, that means you're still exchanging energy, but you're no longer exchanging matter. So something has sealed it off airtight. Okay, so kind of like this. Let's say you go to the grocery store and you buy like a steak. Okay, you take the steak out of the packaging and put it on the counter. In that condition, steak is an open system. It can exchange matter and energy with the surroundings, but you want to put it in the freezer and save it for later. So you put it in a Ziploc bag. Okay, you seal it shut. Can it exchange any matter anymore? No, but when you put it in the fridge, or in the freezer, is it going to freeze? Because it's going to give its energy to the surroundings, the inside of the freezer. Okay, so a closed system doesn't exchange any matter. It's sealed off airtight. Those are easy to build, but it still exchanges matter. Okay, isolated systems are basically theoretical. Okay, it is always possible to seal matter off from a system, but it is not possible to seal off the energy. Okay? Energy is not matter. Energy can travel through solid walls. Okay? It's not a material, so it doesn't have to follow those rules. It is not possible to perfectly isolate something from its surroundings. Okay? So can everybody follow me there? Because I often have people that say like, well then the International Space Station is like completely sealed off from its surroundings. Is that true? No. It's got tons and tons of solar panels. It's absorbing energy from its surroundings. Okay? It also bleeds heat into the vacuum of space. Right? That's why they have to keep the heaters on and all that kind of stuff. And supplies continually have to be brought to it from Earth. That does definitely not make it an isolated system. Okay? Isolated means it doesn't exchange matter or energy with the surroundings. In other words, if you could actually completely isolate something, it would be invisible. Okay? Because it wouldn't emit any light. Light is a form of energy. Okay? So you wouldn't be able to see it. Does that sort of make sense? Okay? So that's not possible. It's not possible to isolate something off from energy. Is it possible to insulate something? Yes. Insulate is different than isolate, right? Like for my coffee cup, right? That's not an isolated system, even though it's sealed off, okay? Assuming it's airtight. Is it still going to exchange energy with the surroundings? Sure, it'll keep my coffee warm for a few hours, but I can already feel that up here where the insulation's a little thinner, it's warm, okay? The lid, that's like the Achilles heel of all the Yeti, okay? Because their lid is plastic, it's hot, okay? That means it's exchanging energy with its surroundings, okay? And of course, every time I take a drink out of it, it becomes an open system because I'm taking some away. Okay, making sense? Okay, that's the difference. Got to know the difference, got to be able to identify what type of system we're talking about. We use isolated systems in physics all the time because they're simpler. Okay, so we just imagine that there's nothing else going on in this system except what we want, just for simplification purposes. Okay, so first law of thermodynamics, okay, is the law of conservation of energy. Okay, so it's important to distinguish heat from work. Okay, work involves the movement of matter from one location to another, whereas heat is a transfer of thermal energy from one location to another. Make sure you write that down. That is the difference between work and heat.
Can we please get the junior boys volleyball team down to the cafeteria for your team picture? Thank you.
Okay, heat transfers thermal energy, work transfers mechanical energy, which is why it can move objects from place to place. Okay. Okay, so right now, because all of you are open systems, okay, there is a transfer of thermal energy, heat, emanating from you, okay, because you're warmer than the surroundings. Okay, this is why if you are trying to rescue someone who has hypothermia, okay, what you're supposed to do is like hold them really close to you because you're hotter than they are, okay, and your heat will naturally move to them to try to warm them up. Okay, sort of makes sense? This is also how lots of sort of insulation would work as well. Okay, insulation, we're trying to keep the heat from going away from us, and there's ways that it can do that. Conduction, convection, and radiation, which you probably learned about in junior high. Okay, we want to prevent those things. We want to keep them in. Has anybody ever used the emergency blanket or seen the emergency blanket that they give people like from the ambulance, or sometimes they're in your car's emergency kit? What are they made of? It's just tin foil. Okay, it's just a piece of tin foil big enough to wrap yourself in. Okay, what does tin foil do? It's no insulative value whatsoever, right? It's not an actual blanket, okay? Like it's not soft and anything like that, okay? But it's shiny. What is it doing to your heat? Keeping it in by reflecting it back at you. Okay, that's all it's designed to do, is keep your radiant heat, okay, that you would naturally lose to the environment, reflected back at you. Okay, like literally try it sometime. Even if there's just the tin foil in your house, wrap the shiny side around your hand will start getting hot. Okay, it'll literally reflect all of the radiant energy that comes from that part back. Okay? That's why we wrap a potato in it if we want to bake a potato. Right? That way all the heat inside will go into the potato, but it can't get out, and it'll reflect and bounce around and cooking the potato faster. All right, so heat, transfer of thermal energy, work, transfer of mechanical energy. So heat doesn't really move objects, okay? I mean, you can sometimes feel a current of air as a result of that, but that is actually heat turning into mechanical energy. Anytime it starts to actually move a material, it's becoming mechanical energy. Okay. Okay, so heat flows from high energy to low energy. So the person on the left there, that's fairly obvious. If you put a metal rod in a fire, don't hold it like she is. What should she be wearing? Gloves. Yeah, metal conducts heat very well. I would not put a metal rod in a fire and then grab one end of it with bare hands. Okay, that's a recipe for disaster. Okay, but if she puts the hot end in a bucket, okay, what happens to the water in the bucket? Right, will it boil real quick? Does it sizzle and pop when you stick it in there? Okay, well that's because it's transferring its energy to the water. Okay, there's enough of it there to vaporize some of the water immediately. The rest of the water will get hotter. Right? Okay, so that's showing that energy always flows from hot to cold, but the same is true for mechanical energy. It is naturally going to flow from a high energy object to a lower energy object. So this person here, they get on this like pogo stick here, right, which is basically either a spring or a set of elastic cords. Okay, to get it going, you have to jump in the air onto it. Okay, so it's on the ground, I jump into the air. Who has more energy, me or the pogo stick? Me. I'm moving, right? I'm elevated above ground level. When I hit that pogo stick, I'm going to stretch the elastic parts of the pogo stick and do work on it. Energy is always going to flow from the higher energy object to the lower. Now, with that pogo stick, once I stretch the spring or the bungee cords, okay, and I'm now down as far as it can go, now which one has more energy, the stick or me? The stick. I've done all the work and transferred all my energy to the stick. Now those bungee cords or spring are going to push me back up into the air. That's how a pogo stick works. Okay? If it was an absolutely isolated system, once you jumped on it, it would bounce forever. Okay? Obviously they don't do that because it's not an isolated system, and it's always losing energy to the surroundings as sound and heat and things like that. Okay, making some sense? Okay, so I want you to write down the first law of thermodynamics there, okay?
Please excuse interruption.
Okay, so the first law of thermodynamics basically says that energy can't be created and it can't be destroyed. In other words, the energy in a system remains constant. Okay, so if this was a perfectly isolated system and there was no air resistance or anything to the pendulum here that I'm swinging, okay, it would swing forever, okay, because it could never lose any energy. It would just constantly convert potential energy into kinetic energy, and that would be 100% efficient, and the thing would just swing forever. Okay, obviously that's not the case. Okay, I have to keep putting just a little bit of energy into it all the time to keep it going. Okay, if I stop doing that, you can already see it's not swinging nearly as far as it was just a few seconds ago. Okay, so if I want to change the energy of this system, I have to do work. Yeah, okay, so that means I got to move my hand. I got to exert a force on this pendulum to get it swinging faster or higher. If I want it to swing even higher, then I got to put a little bit more work into it. Okay, I've got to keep adding energy to the system. I can do that. Okay, in the absence of any heat or work, the energy of the pendulum would stay the same. But I can change it if I want to add energy. Or, if it's not a perfect system, it'll lose some. Okay, but the fact of the matter is, it's always accounted for. It's either in the system or it's in the surroundings. It's never gone. Okay, that's that whole energy can't be created and it can't be destroyed. The amount of energy present in the universe is constant. Okay, it's just turning into different forms, but it's always there. All right, everybody okay with that idea? All right. No, don't worry about that part. We don't need that. Okay, how many people have heard of one of these things? A perpetual motion machine. Okay, it's a machine that's supposed to be able to run forever. Okay, doesn't need any energy, just runs forever. All right, why is that not possible? I mean, think of that pendulum. As soon as I stopped pushing on it, what did it do? It quit, right? Because there's always energy flowing away from a higher energy object. That pendulum was a higher energy object than its surroundings. So energy was constantly going to the surroundings. You can't make a machine that is 100% efficient. It's always going to lose energy to the surroundings. There's no way to eliminate things like friction or air resistance or things like that, okay, from the equation. So a perpetual motion machine will always eventually stop, no matter how efficient you make it. Now, even if you could make a machine that could run forever at 100% efficiency, what could it never do? Four-letter word, starts with W. Work. A perpetual motion machine, even if you could make it, could never do any useful work. It could just run. But as soon as you attached it to something to make it power it, it would quit. Because in order to do work, you have to lose energy. You have to give it to the other thing. Well, if I'm not putting any energy into the perpetual motion machine, it can't give any away or it'll stop. Okay? Otherwise, I'd be creating energy, right? And the first law of thermodynamics says I can't do that. Okay? So, perpetual motion machines are basically forbidden in physics because of the laws of thermodynamics. They can't do any useful work because that would require them to create energy, and nothing is 100% efficient. Energy always flows from high to low. It's always going to flow away from the machine. Okay? Now, people had ideas. Okay? They had ideas about how they could make a perpetual motion machine. These were two of them. Okay, so the first one was this wheel, okay, with these like ball bearings in it, and it was kind of like slices of pie, except they were slightly bent, slightly arched. Okay, so the idea was that as the wheel spun this way, the ball bearings would go out to the edge. There would be more force or more torque from them that would rotate this thing down, but when they came up on this side, they would roll back towards the middle where there would be less torque from them, and this thing would just continually run. Okay? Where is it going to lose energy? Marcus?
Friction balls against the metal pieces.
Yeah, first there's friction from the balls rolling. You'll be able to hear them, right? And if you can hear them, that means they're losing sound energy. Okay? But it's also rotating right here in the middle. Will there be friction there? No matter how good you make those bearings that thing would be rotating on, okay, there's going to be friction there as well. This thing won't run forever. Now, the one on the right, I kind of like. Okay? I feel like it had more promise because it was using a what? A magnet. Now, that's just like a horseshoe magnet. It's not an electromagnet, so I'm not putting any energy into here. Okay, so yeah, that ball bearing would be attracted to it. By magnetism, it would go up and then it would fall through the hole and come back down. But every time it gets to this door, it has to do work. Okay, now technically, I am putting energy into this system. It's a bit of a cheat because there's a magnet there. Does a magnet stay magnetic forever? They all eventually, and this is not like a short-term thing, it's a long-term thing. It would be years, okay, before that magnet would lose its magnetism, but they don't stay magnetic forever. All right, so second law of thermodynamics, so get you to copy that one down, okay? That describes the energy, the direction of energy flow in natural processes. That is high to low, hot to cold. That's the second law of thermodynamics. Okay, everybody good with the second law there? Okay, just that energy always flows from high to low, hot to cold. Okay, but it'll never go the other way. You can't get heat energy or thermal energy from something colder than you. It will not flow that way. All right, so the second law of thermodynamics allows us to kind of harness how thermal energy moves. Because usually, when thermal energy starts to move, it'll convert to mechanical energy and move matter along with it. Okay? This is the idea behind the heat engine. Okay? Very simply, a heat engine looks like this. You have a high temperature area, probably where you're burning a fuel of some kind. Okay? You have some sort of a turbine or something here, okay, that matter is going to flow through as it moves along with the energy from hot to cold. Okay? Because heat has to do this. Right? There's nothing that can stop it. So all you try and do is put something in between the hot and the cold to harness some of that flow and get mechanical energy output from it, or work. Okay? What kind of engine do we commonly see that is a heat engine? Combustion engines are sort of. We do use the thermal energy to cause expansion, but there's one that actually more directly does this even. Not going to be on anything you drive on a road. Steam engine, same thing. It's still using like a expansion of gases. This is how a jet engine works. Okay, a jet engine is almost perfectly.
Excuse the interruption. Could senior girls volleyball and girls soccer come down to the cafeteria for your pictures? Thanks.
A heat engine. Okay, so you've got the big intake at the front, right? Everybody's seen what that looks like, right? You don't want to get sucked into that. Okay, if birds get sucked into that, it can destroy the engine, because inside of there are all these very fine, thin aluminum blades. Okay, and these aluminum blades are all kind of angled. In the heart of the engine is where the jet fuel is burned. Okay, and jet fuel is really just kerosene. Okay, it burns really, really hot. So you get all this heat in the middle of the engine, and air tries to move through the engine because the heat wants to go from hot to cold. So as long as those turbines are spinning, air gets sucked in through the front, heated, and then it wants to rapidly escape out the back, turning those blades and creating thrust. Okay? But it is at its very heart a heat engine. It is just using the fact that energy wants to flow from hot to cold. So it makes one area very, very hot. And then if you're flying at 30,000 feet, okay, it's very, very cold all around it. The surroundings are all very, very cold, so the heat is just pushing air through there. And the more fuel you burn, so the higher the throttle, the more thrust you're gonna make, because the more heat wants to go out the back of that engine. Okay? And it'll create thrust that pushes the plane forward. Okay, now, so this little part here, according to the second law of thermodynamics, heat never flows naturally from cold to hot. You don't necessarily need to write that because it's kind of already up there. Okay, heat can be made to move from cold to hot, but you have to do work to make that. It's like active transport. We'll talk about that in a minute. Okay, so the original idea for a heat engine, okay, was this. So it was with a boat, okay, and it was like a deep ocean kind of boat. So water at the surface of the ocean is warm. Water at depth is much colder. Okay, so what they thought was if we had a tank that had surface water in it, so a short pipe there where surface water would come in, and a really, really long pipe that went very, very deep into the water, okay, this tank would fill with cold water. And naturally the water would want to go with the heat, okay, through this turbine, which would then turn and propel the plane, or propel the boat forward. I mean, theoretically, that's, you know, sort of sound, I guess. Practically speaking, I wouldn't want to be in a boat that has a pipe that goes all the way to the bottom. It feels like that's a recipe for dragging something on the ground and then pulling out a big section of the boat and sinking. The ocean scares me. Okay, so I would definitely not sail away on a boat like this, okay? But theoretically, it would work. The only problem is this warm water already in contact with cold water? What's its motivation to go through the motor? Basically none, right? It can already circulate with itself. So it wouldn't work very well, plus this temperature difference isn't very big. If you want a heat engine to work, you need really, really hot and really, really cold. Okay, the bigger the difference, the faster the flow will be. This isn't a huge difference. So it's kind of like saying, you know, I got a mouse here and I got cheese here. The mouse can go through the maze to get to the cheese or straight to the cheese. What's the mouse's motivation to go through the maze to get to the cheese when they can go straight there? What's the energy's motivation to go through the motor when it can already make contact with it? Okay? So it's theoretical, yeah, sure, it's fine, but practically speaking, not going to work. Okay, now, here's another example of kind of a sort of heat engine, sort of Newton's, or sorry, second law of thermodynamics. Okay, this is a hot water heater for a little hot tub. Okay, but you use a wood fire to make it work. Okay, now this hot tub, when we got there, it was like there was a layer of ice on the top of the hot tub. Okay, so it was like ice cold water. The water goes through these pipes here, okay, and into this thing, and then you got water surrounding the fire, and then obviously the chimney kind of comes up in between. Okay, so I lit the fire, and the water started to heat up. Now, you'll notice there's a pipe on the top and a pipe on the bottom. Hot water would travel through this pipe and into the tub, and then it would get colder and it would sink, and it would come back through the lower pipe. It started flowing exactly like you would expect. And over the course of only a couple of hours, that was too hot to get in. Okay, it was like literally about 50 degrees or so. Okay, it was like, it hurt to get in, so we had to dump some ice in it just to cool it off. Okay, but all it did was use the second law of thermodynamics. This was hot, okay, the water went from hot to cold, okay, the cold water dropped, came back in towards the hot, okay, and it just kept flowing. All it did was use the second law of thermodynamics, simple design. Okay, and it didn't need a pump. but you could actually feel the water coming out of the hot pipe and going into the cold pipe when you were in it. It was flowing through with no pump. The second law of thermodynamics was making it go all on its own. Okay? See, this is how much of a nerd I am. I saw this, and what did I do? I took pictures and explained to my wife how it worked. And she gave me this look. That happens sometimes. Okay. All right, so second law of thermodynamics in action there. Okay, jet engines. So a jet engine is an example of a heat engine, right? You got that hot gas, okay, being kind of created in the middle, okay, and then air wants to flow through here. That turns the turbine, okay, which creates thrust, also generates electricity for the plane, right? Now, the opposite of a heat engine is a heat pump. So your refrigerator and an air conditioner are both heat pumps because they go against the second law of thermodynamics. They're taking heat from, let's say, your house and pumping it out to the outside, which is hotter than inside your house. They're making it go the other way. But in order to do that, you have to use energy. So that's why I was saying a heat pump is like active transport. A heat engine is like diffusion. It's just letting things go the way they would normally go, hot to cold, okay? But to make it go the other way, you've got to put energy in or put work in to make that happen. Okay, so the way your fridge, or sorry, the heat engine here, so let's talk about the heat engine. So this is a thermoelectric converter, like a thermocouple, like we talked about the other day, okay? All they've done is take two beakers, one that's 90 degrees Celsius, so water right out of the kettle, and one that's 10 degrees Celsius. Okay? You put the leads in the hot and the cold, okay, and that engine will spin. How long will it spin for? What happens when the temperature of the two waters is the same? Then there's no flow anymore, right? This only works as long as there's a temperature differential. So a heat engine works as long as there's a temperature differential between hot and cold. Once those temperatures get even, then it's like osmosis. Then it goes in and out equally and nothing happens. Okay, everybody with me on that one? Okay. All right. So your refrigerator, okay, is a heat pump. All right, so I'll get you to copy down what's in or underline there, please. Okay, I'll give you a couple minutes to do that, and then we'll talk about how your fridge works. Okay, so a heat pump, like we said, actually goes against the second law of thermodynamics. It makes heat go from cold to hot, which it would never naturally do. Right? So if it's something it wouldn't naturally do, then we've got to put work in to make it happen. So your air conditioner and your refrigerator work the same way. They have coils of copper pipe. Inside that copper pipe is refrigerant. Okay? It's a special compound.
Please excuse interruption. Could we please have video game club and music ministry down to the cafeteria for your photos?
Okay? It's a compound that easily changes state. Yeah, go ahead, guys. Easily changes state from liquid to gas around the temperature you would keep your refrigerator, okay? And if it's the air conditioner, it's just in a kind of an air cavity inside your furnace usually, okay? So what happens is you put warmer food in your fridge. Okay, let's say it's your leftovers, right? Like you got done eating, it's still a little bit warm, you put it in the fridge. Okay, well, that heat is going to radiate off of it. And there's pipes that run through the walls, okay, and the ceiling of your refrigerator. The heat goes to those and it's absorbed by the refrigerant. The refrigerant turns from a liquid to a gas. It takes about 230 joules of energy for the refrigerant to turn from liquid to gas per gram. Okay, so if I want to change 1 gram of refrigerant from liquid to gas, it'll absorb 232 joules to do it. Okay, now that gas goes through the pipes down to the compressor. Okay? The compressor is the thing that you can hear running when the fridge is running. Right? And the compressor does exactly what its name would imply. it applies pressure to the gas. Okay? When you force a gas back into its liquid form under pressure, it releases all the heat that it absorbed. Okay? So this forces it back to a liquid and the heat gets released. That's the warm air you feel coming out from underneath the fridge. Okay? That is released from the refrigerant by the compressor and then blown out by a fan into the surroundings of the refrigerator. Okay? Takes a lot of electricity. So does your air conditioner. I mean, your refrigerator is only cooling a volume of air of about maybe 30 square cubic feet, maybe something like that, right? It's not a huge amount, okay? But your air conditioner has to cool all the air in your house, okay? So it uses a lot more electricity. That's why it's such a big thing outside of your house. But it's doing exactly the same thing. It's running the air from your house past these copper coils. Okay? The refrigerant turns from a liquid to a gas and then goes outside. Outside is where the compressor is. It's the thing that's in the middle. If you ever look down inside your air conditioner, there's like a big kind of hole almost in the middle. That's the compressor. Okay? And it's forcing that refrigerant back into a liquid form. Okay? And if you put your hands over top, you can feel the warm air coming out of the air conditioner when it's running. That is the heat that was just in your house. Okay? But it takes a lot of energy to do that. Okay? We're allowing that heat to turn something into a gas, and then we're compressing it back and pumping the heat out. Okay? Everybody good with that? So a heat pump goes against the second law of thermodynamics. A heat engine uses the second law of thermodynamics. Okay. I'll show you how the internal combustion engine worked. Okay, so originally when we were, and there's never going to be any questions about these engines, guys, it's kind of just for interest's sake here. The first idea of the heat engine where you could use expanding gases to do work was the gunpowder engine. Okay, as its name would imply, it could be fired once. Okay? You would explode the gunpowder and the piston would go up, and then you would have to reset the whole thing. Okay? Early steam engines worked like this one, okay, where you would heat up the whole thing, the steam would move the piston up, and then you would have to throw water on it to cool it off so the piston would go back down. Okay? They didn't run continuously, okay, like engines do now. Okay? Technology wasn't there yet. Okay. For a typical internal combustion engine, this is what it breaks down to. Okay, so if you remember yesterday, I said that an internal combustion engine is a 4-stroke engine because there are 4 different cycles or movements of the piston. Okay, so in order for this to work, right, you have to have what's called an intake phase. So the piston comes down and there's valves at the top. Okay, so when the piston comes down, it actually pulls air in. Okay, it creates a vacuum and pulls air and fuel, okay, probably from your fuel injection manifold, okay, into the cylinder. Okay, then when the piston tries to come back up, the valves close and the gas gets compressed, okay, making it far more volatile. Okay, at the top, the spark plug fires and the gas is ignited. Then there's the expansion of those gases. That's the power stroke. Okay, that's where heat gets turned into mechanical energy. Right? And then there's a final cycle where all the spent gases go out through the exhaust valve. Okay, so it's pushed up. So it actually has to do 4 different strokes, okay, in order to have intake, compression, ignition, exhaust. Okay, but it's converting heat into mechanical energy. All right, leave it there for today. Remember, none of what we did yesterday or today is on your unit exam on Monday. None of it. Don't go over this stuff on the weekend. Just the stuff in the review package. Just biology. Okay? Probably do that practice test today or tomorrow so you know what you need to look at on Sunday. If you want to start early, be here at 10 after 8 on Monday. I'll let you start at 10 after 8.
I want photos.